So we finished up last time, so first by stating theorem 4.12 and then deducing from it theorem 4.13, which is our scaling limit theorem for, so this is a BNMA tree conditioned to have n vertices in total. So remember we had a critical offspring distribution with finite variance, okay? And we showed this form of convergence of this metric space with its sort of natural uniform measure on the vertices to the Brownian continuum random tree. So possibly a few observations are in order about this convergence. This is really quite a strong notion of convergence. If I want to know things like extreme distances in this tree, this is converging. So suppose if I take the diameter of this metric space here, this is a sufficiently strong form of convergence that I get convergence to the diameter of the right-hand space. Okay, so this is really sort of everything I could want to know about this thing as a metric space. Okay, so we've already seen the theorem due to K, which gives this convergence of the first coordinate here, this convergence of the Łukasiewicz path of my BNMA tree here. So in fact, it's going to be sufficient for me to show that if I get the right scaling constants in front, if I take the difference of these two processes and I look at the maximum of that difference over the whole of this interval, then that thing is converging in probability to zero when I scale it correctly. Okay, so that's actually the form that I'm going to prove this theorem in. So I'm going to prove, so theorem 4.12, and I'm going to prove it in a special case. I'm going to assume that we've got a finite third moment for the offspring distribution psi. So there are a number of people in this room who I know have seen this theorem before. I think you haven't seen this proof because I only wrote it down a month ago. So I hope that there will be some interest here even for those people who've seen some version of this before. Okay, so in the case, so as I said, the first proof of this theorem due to Marker and Mokadem assumed an exponential moment. I'm assuming a bit less than that, so I just want a third moment. So let me define Rn of k to be what I'm going to call the remainder when I take sigma times the height process and I subtract off it 2 on sigma times the Łukasiewicz path. Okay, and that's for k between 0 and n minus 1. Okay, so the form that I'm going to prove this in is as fact as follows. So let me fix an epsilon which is positive. So then there exists a constant A which is strictly positive, such that if I look at the probability that the maximum of this remainder over all of the tree, and this is a quantity which can take both positive and negative values, so let me put the modulus. So the probability that that exceeds epsilon root n. So I just want a convergence in probability, but I'm actually going to give an explicit upper bound here. So this is less than or equal to A on epsilon to the power 5. The power here is not very important, square root of n. Okay, so in particular, if I let n go to infinity, this in particular provides me with a convergence in probability to 0 as n goes to infinity. Okay, so in particular, I get that 1 on square root of n times this maximum. So in combination with K's theorem, that's certainly enough to get me the joint convergence in distribution. Okay, so I need to do a little bit of setup before I can get to the proof, because the way I want to think about this thing is really in terms of branching random walks. So that's probably a model that lots of people in this room have already come across, but let me kind of set it up from the get-go. So let's have a little section on branching random walks. And I want to take quite a general framework. So I'm going to start by just fixing a deterministic tree, which is one of my rooted ordered trees. Okay. And I'm going to think about associating displacements to the edges of my tree. So to edge, let me use the Ulam-Harris labels. So an edge from U to the ith child of U, okay, and then I is going to vary between 1 and the number of children of U. So to those edges, associate displacements which in general are going to be random variables, which are going to be called du, ui. Okay, so hopefully the notation is reasonably clear. So these are going to be random variables which may depend on the number of children. Okay. But the displacements from different vertices will be independent of one another, right? So it may be that the displacements of different children of the same vertex are dependent, but if I look at the children of two different vertices, the displacements of those two sets of children will be independent of one another. Okay, so I've got independence from different vertices and potentially dependence from a single vertex. So, and then displacements from different vertices are independent. Okay, so let's have a quick picture of what this might look like. So I've got my root here, and suppose it's got 3 children. So 1, 2, 3. Okay, so let's give this one displacement -1. This one can have displacement -2, and this one can have displacement 5. So, okay, and then let's have a look at the children here. I suppose there are 2 of them of the vertex 1. This has got displacement 0. This has got displacement 15. Okay, and so on and so forth. So my requirement is that displacements away from distinct vertices should be independent. And apart from that, this is quite a general setup. Okay, so the simplest case is when you just think about taking every single displacement in this tree just to be a copy of an IID random variable. Okay, so that's the sort of vanilla branching random walk, is when you just have IID displacements along all edges. And I want something a little bit more general than that, but that's maybe the model to have in mind. Okay, so I'm going to use these displacements to give me positions for the vertices. And how do I get the position of a vertex? I look from the root along the ancestral line of that vertex, and I sum up the displacements. Okay, so positions. So I'm always going to sort of anchor my tree at 0. So the root is always going to be at position 0. And then I'm going to add up, for any vertex u which is not the root, all of the displacements along its ancestral line. So in particular, this is going to be the displacement from empty set to u1, plus the displacement from u1 to u1, u2, whatever that is, all the way up to the displacement from the parent of u, let's say um-1 up to u. So that's if u is in generation m. Okay. So is it clear what the construction does? I just sort of sum along ancestral paths. Okay. So what I'm going to do is I'm going to apply this construction to my conditioned Bienname tree. Okay. So now the genealogy that I'm taking of my population is a conditioned Bienname tree, and I'm going to put particular displacements along the edges. Okay, so for the moment this is a branching, so I've got the tree being fixed and the displacements being potentially random, and now I want to think of the tree being random and the displacements also being random. And notice that because I'm allowing my displacements to depend on the number of children of a vertex potentially, that means that these two things are quite dependent. Okay, so if I do this with requiring independence between the displacements away from different vertices, then if you think about what's happening along the ancestral line to a particular vertex, really what I'm doing is I'm summing up independent random variables. They're not necessarily identically distributed, because the distribution can depend on the number of children at the particular vertex, but they're independent of one another. Right, so I'm getting a sort of random walk to each vertex. And let me give myself a few more vertices in my tree. Suppose I think about the positions of two, well, that's actually a bad choice. Let me do this and this. Okay, so if I think about the positions of these two vertices, they share common displacements up to the most recent common ancestor, and then I've got independent evolution. Well, so here I've got dependent evolutions, but here this is independent of what's gone before. So up to the most recent common ancestor, I get sort of displacements which are identical and then dependent, and then finally they get independent of one another. Is the picture reasonably clear? Okay, so let me remind you that we had V0, V1, all the way up to Vn minus 1, being the vertices of my tree listed in lexicographical order. Okay, so I also want to think about listing the positions in that same order. So I'm just going to ask, what's the position of V0? Well, that's the root, so that's 0. What's the position of V1? What's the position of V2? And so on and so forth. So that gives me a process of positions, which is PVK for k between 0 and n minus 1. Okay, so that's the process I'm going to be interested in. Okay, so this is an object that's known in the literature as the head of a discrete snake. Okay, so you don't really need to know what a snake is in order to understand what I'm doing next, but for those of you who have seen snakes, this is an example of the head of a snake. So roughly speaking, what's the idea? If you think about doing this lexicographical exploration of the tree, what happens to the position as you move from one vertex to the next? Well, the chances are you've got some common bit of path. Okay, so I'm thinking about the positions along the ancestral line as being kind of the positions of my snake, right? So it's wiggling, it's got some wiggly positions. Okay, and then I'm going to move to the next vertex in lex order. And what's probably going to happen is the sort of top segment of the snake is going to move a bit. Okay, so that's why I'm calling the vertex at the top, the position of the vertex at the top is the head of the snake, right? And you can think that this is sort of wiggling in and out as we explore through the tree. Okay, so I'm just going to be interested in the value right at the head of the snake. Okay, so, there's a whole theory of these things. They were introduced in particular in the context of, Le Gal's constructions of superprocesses with the Brownian snake, and this is a sort of discrete version of that. So if you've seen some of those things, this is genuinely quite linked to that, although I'm not going to make use of that link directly. Okay, so I'm going to apply this construction with a particular set of displacements, and the first thing I need to show you is why that's related to this process Rn. So apply this construction with displacements so the displacement from a vertex u to its ith child is going to be deterministic given the number of children, and it's going to be given by sigma minus 2 on sigma times the number of children of u minus I. Okay, so this looks like a super weird thing to do. Okay, so firstly, I'm taking a branching random walk where the only randomness is in the tree. There's no randomness in the displacements. Okay, so that's already a pretty odd feeling thing to do. And then I've taken a very strange looking set of displacements. So what I want to do immediately now is justify why this is the right thing to do. So this sigma and this 2 on sigma are these sigma and 2 on sigma. Okay, so there clearly is going to be something related here. So firstly, what's this? So if you think about sitting at the ith child of vertex u, this is the number of younger siblings. Okay, so this is the number of younger siblings of the vertex ui. Okay, so that's got something to do with the Wikasiewicz path, because remember the Wicasiewicz path up to a point is go down the ancestral line and count out how many younger siblings of myself or one of my ancestors there are. Okay? And so when I sum this down the ancestral line of a vertex, that's precisely what I'm doing. So here I'm just summing up one for each generation. So what does that do along the ancestral line? That just gets me the height. Okay? And when I sum these guys up, I'm summing up the number of younger siblings of a particular vertex down my ancestral line. So when I sum all them up, back down to the root, I end up with the value of the Wicasiewicz path. Okay? So this is exactly the right thing in order to capture this difference, Rn of k. Okay, so let me write some of that down. So recall from, I think it was exercise 3.7 in the notes, that xn of k is the number of younger siblings of vk or one of its ancestors. Okay, so maybe let me go over here. I should probably leave the statement of the theorem up, shouldn't I? Okay, so then, if I take a value of k that's between 1 and n minus 1, so I'm not looking at the root, then p of vk, so this is just sum along the ancestral line of vk, so one way of writing that is using, so I want to include the, no, let me include vk. Okay, so I want the displacement from the parent of v to v at each step. Okay, so then that gives me precisely, so sum up 1 for each edge along the ancestral line, so it gives me sigma times the height. And if I sum up these numbers of younger siblings, as I said just now, I'm going to get 2 on sigma times the value of the Wicasiewicz path. Okay, so that's precisely my Rn of k. Okay, so I can interpret this distance, or this difference, actually as the value of a branching random walk at particular points in the tree, where my branching random walk is a pretty peculiar branching random walk. Okay? So what I'd like to show you is that this branching random walk nonetheless actually has some quite nice properties. Okay. So maybe I should note it's certainly also the case that p of the empty set, which is of course the same as p of v0, is just 0, which is indeed the value of r at 0. Okay, so it matches up there as well. Okay, so the thing I'd like to deal with is the maximum modulus of this thing. And I want to split that into 2 parts. So I want to think there's a maximum positive difference and a maximum negative difference, and I want to deal with those separately. So let me define Rn plus, which is just going to be the maximum without the modulus. And then I'm going to take Rn minus to be the maximum of minus Rn of k. Okay, and it's going to be easier for me to deal with those separately, essentially because this thing is additive, right? So it's going to be nice to be thinking about it without the modulus sign random. So it's clearly sufficient for me to prove this theorem here with, instead of this thing, I can replace each of those things in and then use a union bound. Okay, so clearly sufficient to prove the theorem with replaced by plus or minus. Okay. So my notation at the moment is a little bit heavy. So let me give ourselves something that's a little bit simpler. So I'm going to be particularly focusing on what happens at the root. So I'm going to use this recursive decomposition at the root that we saw last time. And so in particular, let's have some lighter notation for the displacement specifically away from the root vertex. So remember, the root vertex has got Cn children. Okay, so let me write di in place of d empty set I for I between 1 and Cn, where remember this was the number of children of the root. Okay, so let's immediately just apply that recursive decomposition and see what it gives us when I think about, say, the random variable Rn plus. Okay, so maybe let me have a picture at the same time so that we can talk our way through it. So suppose I've got 3 children of the root, each of which, of course, has its own little subtree. Okay, so what have I got for this maximum? So it's going to be the maximum of 3 things in this instance. It's going to be the maximum of first displacement plus the maximum of a smaller version of this Rn in this subtree. Okay, taken with, well, I've got a displacement plus a largest positive displacement in this subtree, and then a third one here. And I want the maximum of those 3 sums. Okay, so let me write that down. So in general, what I get is that Rn plus I can write as the maximum over I between 1 and Cn of, well, firstly, I've got the displacement along the edge to the vertex I, and then I've got, well, a new copy of, so maybe I'd better have some slightly more complicated notation. So I've got a new copy of this branching random walk construction just in a smaller tree, right? And what is that smaller tree? It's got size, remember we had nn1 for the first one here, nn2 for the second one, and nn3 here for the third one. Okay, so now I'm just looking at a smaller copy of the same problem. Okay, but if I condition on the values of Cn and nni, then this is just a new independent copy for each of these subtrees. So the subtrees only depend on one another through their sizes. And apart from that, they're just new conditioned Vienna matrices of the particular size that I've been given. Okay, so I've got this decomposition into bits which are sort of basically independent of one another if I condition in the right way. Okay. So there's a similar decomposition for Rn minus, but we need to pay attention to something, which is that while it's the case that, suppose I only have a single child. If I only have a single child, then its displacement is just going to be sigma. Okay? So I always have a vertex, well, I always have a child with a positive displacement away from me. Okay? So it's always good for me if I'm seeking for this maximum to go into a subtree, right? Because I always gain something. On the other hand, there isn't necessarily a child with a negative displacement. And so it is theoretically possible that the maximum negative displacement in the whole tree is actually at the root. Okay? So that means I need one more element here, which is I just need to take a maximum with 0. So this is then the maximum. Get this right. So overall, the children of the root of now, I'm looking at minus it, so I get minus the displacement plus this maximum negative displacement. Okay, so let me write this down, Rmi, Rmi plus and minus. So this is as I gets greater than or equal to 1. And so these are independent copies of, so Rm plus and Rm minus, independent for different m's greater than 1. Yep.
You ended up not writing the 0 back?
Sorry, thank you. Thank you for pointing out the important point. Okay, right. So the point is I want the bits of this thing to be conditionally independent of one another, right? So I've sort of got these extra copies of these RMI pluses, okay, where the index down the bottom is telling you the size of the subtree that it corresponds to, and the I up the top is just an index so that I've got IID copies of it. Okay, so these are all independent of, so what do I want? Cn and the numbers of children in the subtrees. Okay, so this maximum with 0 is just to take care of the fact that we could potentially just have a tree that only has a single ancestral line which always has positive displacements along it. And obviously that's an event which is going to occur with vanishingly small probability, so it's not in fact going to affect the argument particularly. Okay, so we've got this funny displacement distribution, and I want to show you now why it's an interesting thing to look at, why there's some hope that I might be able to prove this theorem. So let's just think about what's going on among the displacements away from the root. Okay, so let's think about what the expected displacement away from the root is among these children. Okay, so suppose that I just pick a uniformly random child of the root. What's its displacement? Okay, so if I condition on Cn, the number of children, so the displacement I then get of a uniformly chosen child is I've got Cn possibilities, okay, and I'm just summing over the displacements di. Okay, so let's put in what that is. So this is sigma minus 2 on sigma Cn minus I. Okay. And this is a sum we can do, and let me not embarrass myself by getting it wrong live. So we get sigma minus 1 on sigma times Cn minus 1. Okay. So suppose I now take the expectation of that. Okay. So that gives me sigma minus 1 on sigma times the expectation of Cn minus 1. Okay. Now Cn for large n is approximately the size-biased offspring distribution, right? And so its mean is the second moment of the original offspring distribution, which is sigma squared plus 1. So this is approximately sigma minus 1 on sigma into sigma squared plus 1 minus 1. Sorry, that's a sigma down there. So the whole thing is approximately centered. Okay, so if I think about a uniformly chosen child of the root, for large n, the expected displacement of that child away from the root is 0, roughly. Okay? Okay, so that's sounding good. Remember this picture we had that we've got random walks along each ancestral line in this tree. So what this is saying is, at least close to the root, those random walks are approximately centered. Okay, so this is sounding good. Right, we like centered random walks. What about the variance? This is going to go badly wrong soon. Okay, so similarly, so we're centred, so let's just think about the second moment, or approximately centred. The second moment of a uniformly chosen child of the root is going to be, so this. Okay, and again, we can calculate that explicitly. We've just got this little affine function that we need to sum over. Okay, and what we end up with is, maybe not worry too much about this, something. Okay. So this is now a quadratic in Cn. Okay. And so in particular, because I assumed that my offspring distribution had a finite third moment, then Cn is going to have a finite second moment, and this is just going to converge as n goes to infinity to some finite quantity. And I don't really care what it is, I just need that it's finite. Okay, so this is, because we say this is by lemma 4.7, since we have that the third moment of the offspring distribution, so in other words, the second moment of the size-biased offspring distribution is finite. Okay, so that's where the assumption is coming in. So if I think about looking at a uniformly chosen child of the root, what I'm seeing is a displacement which is approximately centred in finite variance. Okay? So if you think about just going through the tree, each time picking a sort of uniformly chosen child of the root, what you're seeing is basically a centred finite variance random walk. Okay? So what's the height of the tree? The height of the tree is right square root of n. Okay? So to a typical point in the tree, that means I should be seeing roughly Brownian scaling, so I should have a typical displacement of roughly n to the quarter. Okay? Now, in this theorem, I don't want to know about a typical displacement. I want to know about the maximum displacement, right? So I want to take the worst case across the whole tree. So I'm going to lose something here, right? So I'm not asking for convergence on the scale of n to the quarter, which would be the sort of typical scaling. I'm asking for something less than that, okay? But basically, the idea is, if I think about looking sort of from the root, okay, so we saw that the subtree sizes are in fact very uneven typically. Okay, so typically, almost all of the mass is actually in a single subtree. Okay, and everything else is just tiny. So the chances are, if we see a split like that, that the maximum is going to be attained in here. Okay, it's just got a very small chance of being attained over here. So in the typical situation, what's happening is I'm actually making this displacement and then asking for the maximum in this subtree. Okay? And so in particular, which subtree is this one? Well, it's got no reason to be any one in particular. It's going to be a uniformly chosen child of the root, right? Because they're all exchangeable. So in particular, this displacement, which was the displacement of a uniform child, really is the one that I'm interested in. Okay? And then I'm saying a little copy of the same problem, but it's not that much littler. Right? So typically this displacement is moving me into a subtree which has size about n still. Okay, and so that's some intuition, hopefully, for why the argument that I'm about to give you will work. Okay, so I'm going to do the proof for Rn plus. It's a little bit fiddlier for Rn minus, partly because of this maximum with 0, but mostly actually because the positive displacements are bounded. And the negative ones are potentially unbounded, and so you have to be a bit more careful. But I don't want to get sort of lost in technical details, and there's no really new idea in the proof for Rn minus. It's just harder to write down. So I think for the purposes of understanding, let's do the Rn plus proof so that you get the idea of what's going on. Okay, so proof of theorem 414 for Rn plus. Okay. So morally, the proof technique that I'm going to use was something I learned from a paper of Bénédicte Haas and Grégory Mermont. They applied it to the height of a Markov branching tree. I think it's a sort of absolutely magical method of proof, and I really wanted to sort of share it with you. So it's a proof by induction, which, when I first saw it, just seemed ridiculous that you were going to prove a tailband by induction. But we are going to prove a tailband by induction. Okay, so proof by induction. On n. Okay, so let me first make an observation. This is a probability, right? So this statement is trivially true for small n just by taking the a bigger. Right? Okay, so for n less than or equal to some, let's say, na epsilon, which depends on a and epsilon, okay, just by taking a larger. If necessary, simply because, well, any probability is bounded above by 1. Okay. So I don't really need to worry about the base case of my induction. So in particular, let me put some stipulations on this Na epsilon that I want to take. Okay, so firstly, let's take an n naught which is sufficiently large that sigma is less than the epsilon square root of n divided by 2. Okay. So I can obviously achieve that for some n and then all subsequent n's. Okay, so this is just going to be the value of my positive displacement is sigma. Okay, so the largest positive displacement away from a particular vertex has value sigma, and I want to make sure that that sigma is bounded above by epsilon root n on 2. Okay, so that's the purpose of that. Okay, so in particular, di is strictly less than epsilon root n on 2 for all I between 1 and cn. Okay. So let's choose our Na epsilon to be greater than or equal to this n0. Okay. Okay, so let's now suppose that we've got some n which is strictly bigger than this value, and that the statement's true for all smaller values. So for all m which are at most n minus 1. Okay. So the point is that because I'm about to decompose into these little subtrees which are coming from the children of the root, and each of those subtrees is at most size n minus 1, I can apply the induction hypothesis within each little subtree. Okay, so I'm going to do the most sort of simple-minded thing I can at this point, which is, well, firstly, let's look at the event the other way around. So let me look at the probability that Rn plus is at most epsilon root n. That's going to be the easier way around to work with it. Okay. And the reason for that is that I'm dealing with a maximum. And it's usually easier to think about the event this way around if you've got a maximum. So this is the expectation. So let's condition on Cn and the sizes of the subtrees descending from the root. Okay, so this is then going to be the product from 1 to Cn of the probability that each of the random variables in the maximum is itself at most epsilon root n. Okay, and this is conditional on, so nnj for j between 1 and Cn, and the value of Cn. I'm slightly amazed I managed to get that on one line. Okay. All right, so all I've done is I've conditioned on Cn and on the sizes of the subtrees descending from the root, And then given that information, I've just got independent copies of these Rn random variables. Remember that the di's, these are just deterministic functions of Cn, right? So I know them at this point. Okay, so I just want to rearrange things a little bit here in this product. So I want to get it a bit more in the form of the induction hypothesis. So if I rewrite things, I've still got this product from 1 to Cn. Okay. So let me move this so this is on the left-hand side. So I've got Rni plus. And so what I want to rearrange it to look like is this event here, right? So I want a square root of nni, right? Because that's the sort of equivalent of my n. And then there's something that's going to play the role of epsilon. Okay, and if you just cancel things off, what you get is this. Okay, and I'm still conditioning on these guys and on Cn. Okay. So all I've done is just rearrange the inequality. Okay, so this is going to play the role of epsilon. Okay, so each of these is at most n minus 1 in size. So I can apply the induction hypothesis here. And that's going to give me a lower bound, right? Because the original statement is an upper bound with the complementary probability. Okay, so this gives me an expectation of a product, okay, of what? So 1 minus, so A divided by square root of nni. Okay, and then what I end up with here, if you think about it, is this quantity. So I've got my fifth power, and I've just, because I've got so much in this, I've inverted it and put it on top rather than having it on the bottom. Okay, and I'm going to put a positive part here, because of course there's no point in having a lower bound on a probability which has got a possibly negative factor in it, right? I can bound it below by 0 always. Okay. So this is by the induction hypothesis, since we know that nni is at most n minus 1 for all I. Okay. Right, so this now is just going to amount to doing a little bit of analysis with this thing. Okay, so the first thing is that I can bound below this product here by 1 minus the sum of these terms, as long as I've got this positive part in here. So this is just going to be bounded below by, the 1 is deterministic, it can come out. Okay. I've also got an A which is deterministic, that can come out. I may as well pull out also a factor of epsilon to the 5, just to try and make this look as much as I can like the original thing. And I'm also going to pull out the factor of square root of n, which is sort of sitting here. Okay, so what does that give me? Maybe I should have done one more step. Let me do one more step in between because it will be clearer what I'm doing. So let me first manipulate this before I do the lower bound. Okay, so let's say that this is 1 minus, let me do what I was just trying to do, which is pull out some of the factors which I'm going to want to keep hold of. So let me write this down, and then we can talk our way through it. Okay, so hopefully everybody agrees that this is a slightly nicer looking expression. So what have I got? So I should have, so square root of ni to the fifth, but then I've got an extra square root of ni on the bottom, and so that just gives me ni squared in total. If you think about factors of root n, there are 5 of them here, and indeed 5 of them here. Okay, I've got 5 factors of epsilon. Okay, and then the rest is just happening, well, I've got rid of the n's, and that's just given me that when I divide through by this epsilon root n. Okay, so hopefully everybody agrees that's the right expression. And I'm now going to do what I'd meant to do, which was to say this is bounded below by the following thing. Okay. So I've now got the expectation on this term. Okay, so I've got this nni on n squared. Okay, and then I've got this factor of 1 minus di on epsilon root n to the power minus 5. Okay, so this is looking fairly promising. So what am I shooting for? I'm shooting for 1 minus a on epsilon to the 5 root n. And I've got the 1 minus a on epsilon root 5, epsilon to the 5 on root n. I just need to show that this thing is behaving approximately like 1. Okay, just need to show. Okay, is it? Yes, of course. Yes. Okay, but for convergence in probability, fix epsilon. You need it to go to 0 in n. So I don't need the same constant. Okay, so there's sort of basically only one thing I can do here. I don't mind the look of this thing, right? Because remember that almost all of our mass typically is ending up in a single block, right? So there's a good chance that this is actually just picking out a single index and giving me something that's basically 1. There's a question at the back. Sorry? Okay, so I need, yeah, so okay, so I want to assert that I can take A independent of epsilon, right, that the epsilon dependence is all in this epsilon to the 5 on the bottom. Yeah, sorry, I got a bit confused there. Yeah, so I want A to be independent of epsilon here. Right. There is some initialization to do, indeed, yeah. Sorry, I will try and... I fear that the version in the notes, the initialization is a little bit sort of hand-wavy, if I can put it that way. I will try to come up with a version of that that's a bit more solid. But my assertion here is that the A does not, in fact, depend on epsilon. Sorry about that. Okay. So as I was saying, I'm not too worried about this term here because I think that sort of basically everything is typically going to land in a single block. So what we need to play around with is this term here. And obviously the leading term here is just a 1. So that's quite encouraging. But I'm going to have some error because I've got this di on epsilon root n. So the sort of obvious thing to do here is to take a Taylor expansion of this polynomial. Okay. So let's do that. So I'm going to expand. So let me use the fact that 1 plus x to the minus 5 is at most, so 1 minus 5x plus, I don't know, 150 works, x squared. Okay, so this works, I believe, for all x greater than or equal to minus a half. At least when I checked it on Wolfram Alpha. Okay, so if I use that version of the expansion, what do I get for my lower bound? I get 1 minus a on, so epsilon to the 5 root n. So expectation, sum from I equals 1 to cn, so nni on n squared. And then here I've got 1 minus 5 di on epsilon root n plus 150 di squared divided by epsilon squared n. Okay. Does that look all right? I've just substituted in the expansion. Okay. So let me rearrange this. There's the bit I want. Okay. And then there's everything else, which I'm going to stick in sort of 3 error terms. So what are those 3 error terms? They're going to correspond to each of these 3 terms here. Okay, so I've got an a on epsilon root n times, well, I've taken a 1 out here with a minus sign, so I get a 1 with a plus sign, minus the first term, which is just giving me, oops, this thing here. Okay. So that we're quite happy about because we've actually got a lower bound on that from something that we saw in the last lecture. Okay, so this is something we're going to be able to lower bound by constant divided by square root of n. Okay, so this is a positive term. So I like positive terms because I'm looking for a lower bound, so I can chuck it away if necessary. The other 2 error terms I'm a little bit less sure about. So I've got a 5a on epsilon to the 6 times n times a thing here which is the sum from 1 to cn of this sort of reweighting term, which I'm not too worried about, but I've got a di. And so the point is the sign of this di could be positive or negative, right? So I don't know whether on average this is giving me a positive contribution or a negative contribution. It could be either. So let's put a question mark. Right? So the best we can do is hope that this is going to 0 faster than that one, so I can sort of absorb it into it, whichever sign it happens to have. Okay? And then the final term is going to be my 150a divided by, so epsilon to the 7 now, n to the 3/2. Okay. So expectation of, so sum from I equals 1 to Cn of nni divided by n squared di squared. Okay, so this is a term that I'm sure, including its sign, this really is negative. So I do have to worry about that if I'm doing a lower bound. But on the other hand, well, let's jump ahead a little bit. I'm hopeful that this thing is going to be bounded because this is looking a little bit like the variance of a typical child of the root, okay, in terms of its displacement. And that's something we saw had a bounded second moment. And I've then got this n to the 3/2 on the bottom, which is going to help me because this thing is going to look like constant on square root of n. So this whole term is like 1 on n, and this term here is like 1 on n to the 3/2. Okay, so I can absorb it into it without needing to worry for large enough n. So really the question mark is about this term here and how these 3 things compare to one another. Michal?
Sorry, it's just a tiny thing, but in the second term which is not 1, is there not supposed to be an epsilon to the 5?
I've got an epsilon to the 5 out the front and an epsilon squared there.
In the first positive term.
Thank you. Yes, sorry, I was a line too high up. Thank you. Great, okay, so we just need to be a little bit careful about some of these things. Okay, so the first thing I want to say is I'd like to be thinking about, let's say, this term in a slightly more symmetrized way. And I can do that because these numbers of individuals descending from each child of the root, these are exchangeable random variables. So I can sort of decouple the dependency between these 2 indices here, right? Because really, the subtree of size nni could be glued anywhere, and I would still be getting the same distribution. So it's not really that I've got sort of terrifically strong dependence between the ith displacement and the size of the ith subtree. Okay, so exchangeability gives me, and I've put a more careful sort of argument in the notes in sort of lemma 415, if anybody's worried about this. So what I want to say is that this is the same, just by exchangeability, as this thing where I now take the symmetrized version of the displacements. Let's say, use different indices to make it a bit clearer. Okay. Right, so all I've done, if you like, all I've done is I've taken a uniformly random permutation of the labels of, say, the displacements. Okay? And by exchangeability, that gives me the same expectation. Okay, so I think we're in pretty good shape here, right? Because we can actually calculate things. So I've now got this term which we know is looking pretty much like 1. Okay, so I've got a thing here, times, this we can actually explicitly calculate. We did it already. That gave us that. Okay, so here I've got a random variable which is bounded above by 1, and which is also converging in probability to 1. Okay, and here I've got a random variable. Well, this thing has certainly got a nice second moment. So this thing is bounded in L2, okay, and so in particular it's uniformly integrable. And so in particular, because I've got that this thing is converging to 1 in probability, and this thing is converging in distribution to sigma minus, so psi hat minus 1 on sigma, but with suitably many moments converging as well, so plus second moments. And this has, of course, got mean 0. So this whole thing tends to 0 as n tends to infinity. Okay, so irrespective of its sign, it's certainly a quantity which is going to 0. So what I want to do is I want to call this thing, let's say, delta of n. Okay? And so then what we know is that delta of n is a quantity that when I look at its modulus, that goes to 0 as n goes to infinity. Okay, so in particular here, I've already got a 1 on n factor out the front. Okay, so we said that this term was looking roughly like 1 on n. Here I've got a 1 on n factor, and I've got something extra which goes to 0 on top of that. Okay, so this goes to 0 faster than that does. Okay. The second term is simpler because it's non-negative, and so it's okay for me just to bound above. So I'm going to do the same trick of sort of symmetrizing. Okay, so that then gets me this times 1 on Cn times the second moment. Okay. And then the point is that this is bounded above by 1, just deterministically, right? And so in particular, this is bounded by this effectively second moment here, and we saw that that converged to beta, which is a constant. Okay. So let me put in the bound that we had from last lecture. Maybe let me put it in red. So we know that this thing here is bounded above by some constant, let's say k2, divided by 2 square root of n for all n sufficiently large. Say n greater than or equal to n2, I think I said. Let's say n1. Okay, so I'm going to want to post hoc take my starting value of n to be higher than this one so that I always have this inequality being true. Okay, so I've got a thing here which is 1 on n in terms of order. I've got a thing on here which is certainly smaller than 1 on n in order and of uncertain sign. And here I've got a thing which is of order 1 on n to the 3 halves. Okay, so the point is that if I can take my n large enough, then I can absorb these two terms into this term and still get something positive, which I then can throw away in order to get the lower bound. Okay, so in particular, if I take my n sufficiently large, then I get the lower bound that I wanted, which is just going to be 1 minus a on epsilon to the 5 root n. So obviously I've sort of taken my n sufficiently large along the way, and what I really wanted to do was do that right back at the start, okay, so that we're on safe ground. But I think at that point it wouldn't have been at all obvious where those values of n were coming from, so I sort of wanted to show you it along the way. Okay, so that gives us a sort of inductive proof of this tail bound. Okay. Right, so I've got this 1 minus, but of course I really wanted the upper bound, which was a on epsilon square root of n, epsilon to the 5 square root of n for the complementary event. Okay, so I've got about sort of 15 minutes left in this lecture. And because we're about to have a break tomorrow and we're going to sort of not think about maths for a day, I thought this might be a good time to try and draw together some of the threads of everything that I've done in the lectures up until now. So we've only really been talking about random trees. In the first lecture, we had this particular model of binary trees that had lots of nice sort of properties. Then we turned to this more general family of bien-aimé trees conditioned to have size n, where we took the offspring distribution to be critical and finite variance. And I'm aware that we've now seen two different definitions of the Brownian CRT, and I need to match them up.
Can you just quickly clarify how this convergence and distribution of Rn implies the key theorem?
So we saw that the Łukasiewicz path, appropriately rescaled, converged to a constant times the Brownian excursion. So that was the theorem of K. Yeah. Okay? Okay, so if I can show that in this sort of supremum sense, if the difference between that and the height process with the appropriate scaling constants in front of one another, when I divide by square root of n, if that converges in probability, then it's also the case that the height function is converging in distribution to the right constant times the Brownian excursion. Okay, thank you for the question. Okay, so let's have there's a longer chapter in the notes, which is called Properties of the Brownian CRT. So I'm not going to have time to go through all of that in the details, but I at least wanted to sort of pick out some particular highlights. Okay, so this is sort of mini chapter as far as this lecture is concerned. So properties of the Brownian CRT. Okay, so let me call the trees that we had right in the first lecture, so Tn2. So let this be the sequence of trees that's created by Rémi's algorithm. And I've just put the 2 there to make sure that we know there's a difference between this and our bien-aimé trees. So these are the sequence of trees in Rémi's algorithm. Okay, so remember that each of these was uniform on the set of planted, plain, binary leaf-labeled trees, okay, with n vertices. Okay, so there's an exercise in the chapter on bien-aimé trees where you're asked to show that this thing is actually effectively a bien-aimé tree with a particular offspring distribution. Okay, so that offspring distribution is just with probability of half I have 2 children, and with probability half I have 0 children. Okay, so if I condition such a tree to have size n, I'm getting effectively this, except that I've got this extra little edge on the bottom. Okay, so what are these things looking like? Something like this. Okay, so notice that as far as I'm concerned, if I'm thinking about this thing as a metric space, I really don't care about these leaf labels. Okay, I'm only interested in distances between vertices, and they're really a convenient tool for counting things. Okay, so if I just think about getting rid of this little edge here, then I really am looking at a conditioned bien-aimé tree. And the point is that since I'm going to rescale all of the edge lengths by 1 on square root of 2n minus 1, I think, this really isn't going to make any difference. So you can see that in the metric space sense, this is going to tend to the same limit. Okay, so that tells me that whatever the scaling limit of my sequence of trees that come out of Rémi's algorithm is, that must also be the Brownian continuum random tree, just by the theorem that we've just proved. Okay, so in particular, we can deduce this. So 1 over square root of 2n minus 1, 1 over square root of 2n, no difference. So let's put 1 on square root of 2n, it's neater. So we get the convergence in distribution as n goes to infinity, again to the Brownian CRT. Okay. But somehow the setup of Remy's algorithm lends itself a bit more naturally to thinking about, well, a uniform measure on the leaves rather than a uniform measure on all of the vertices. So if you like, you know, what were these leaf labels giving me here? Well, this is really just a uniform pick from among the leaves, okay? And if I look at sort of the numbers 1, 2, and 3 here, that's a uniform 3 set from among all of the n leaves of this tree. Okay, so somehow these things are giving me samples from something that's approximately the uniform measure on the leaves here. Okay, I'm taking samples without replacement rather than with replacement, but you can kind of see that if n is large, there's really not going to be very much difference between those two things. The probability that I pick the same thing twice is in any case vanishingly small. Okay, so somehow this setup lends itself much more naturally to thinking about sort of a uniform measure on the leaves. So the thing that sort of feels natural in the context of Remy's algorithm is really this thing. So let me call it mu leaf, okay, where this is the uniform measure on the leaves. Okay, and remember that when we thought about the line breaking construction of the Brownian continuum random tree, what were we thinking about? Well, we were thinking about the distance between 0 and the leaf labelled 1. Okay, so that's really the distance between the root and a uniformly chosen leaf, right? So what I'd like to do is now match these two things up. Okay, so the point is that these two measures here, this uniform measure on the vertices and the uniform measure on the leaves, these are asymptotically indistinguishable from one another. Okay, so one sort of mini indication of that we've already seen is we saw that the measure of the set of leaves in the Brownian tree is 1, right? So if I pick a point from this measure here, with probability 1, it's giving me a leaf of the Brownian tree. Okay, that's not enough to tell you that asymptotically these two things coincide, but it's a little bit of an indication of sort of why that might be the case. Okay, so I've given you in the notes a kind of proof using the sort of Remy perspective on all of this, that these two measures asymptotically match up, essentially by just coupling them for large enough n in such a way that if I pick according to that coupling, I'm usually getting something which is very close by. Okay, so that's in the notes. Okay, so assuming you'll allow me that statement, I then get that this thing also converges in distribution. Actually, almost surely, but let's not worry about that. To the Brownian CRT. Okay. Okay. Again, in the Gromov-Hausdorff-Prokhorov sense. So we had this nice way of looking at things here, which was sort of looking about, you know, what are the distances between uniformly chosen leaves? Or, you know, we had the subtree that was spanned by the root and some collection of k uniformly chosen leaves, or a uniform k set. But like I say, that's pretty much exactly the same for large n as taking k independent picks from among the leaves. Okay, so let me give a definition, because this is a piece of terminology you may come across if you look in the literature. So let me suppose that I've got random variables which are IID uniform 0, 1. Okay. So let's let tk to e, let's let this be the subtree of my Brownian tree. Of, so t to e, which is spanned by the root and the projection on the tree of the points u1 up to uk. Okay, so we've just said with probability 1 these are leaves, okay, because my leaf measure, or sorry, my measure on the CRT gives probability 1 to the set of leaves. Okay, so let me write, I don't know, dk 2e for the induced distance, right? So this is giving me a sort of submetric space. Let's give its induced distance a name. Okay, so the random finite dimensional distributions of the Brownian CRT are the collection of laws of these little subtrees. Okay, so I'm just thinking about these as little metric spaces now. Okay, I'm not worrying about the measure, because essentially the measure on the big tree is everywhere except on this thing, in fact. So it doesn't make sense to think about the projection of the measure, really. Okay, it's not doing anything interesting. Okay, so you should think of this a little bit like, and the name suggests it, the finite dimensional distributions of a stochastic process. Right? So these are things which determine the law of the stochastic process. Okay? And similarly, I'm not going to state it, but there's a theorem saying that under certain conditions, these random finite dimensional distributions are pinning down the distribution of the Brownian CRT. Okay? So notice that what we've got here is effectively, these are just trees with edge lengths now. Like, you can again think about them, if you like, as sort of combinatorial trees with edge lengths. Okay? So we've got a collection of much simpler objects to get our hands on. Okay, so how would I specify the law of such a thing? I could just say, what's the law of the combinatorial shape, and what are the laws of the lengths? Okay, and this is a finite object, so it's easy to do that. Okay, and that's really giving us a good idea of what's going on in this Brownian continuum random tree. And you can think of these things exactly like in the line breaking construction, right? So these are the subtrees that line breaking construction is giving us. Okay, this sequence of refining trees, which gradually get more and more complicated as I glue on more and more of these little sticks everywhere. Okay, these are realizing the random finite dimensional distributions of the Brownian CRT. Okay, so these are precisely the laws of the, trees, let's say TK, created by Aldous' line breaking construction. Okay. Okay. Right, so how can I read this off? Well, I can just use the fact that I've matched up these leaf and uniform measures here, and I can think about taking a limit in my sequence of Remy trees. Okay, so picking uniform leaves in the Remy tree, let's take the root and k uniform leaves. Okay, so what we're saying is that's asymptotically indistinguishable from the root and k uniform vertices. Right, so that subtree spanned must be converging in distribution to the subtree strand by the root and k vertices picked according to this measure in the Brownian CRT, and that's precisely this. Okay, and we saw in the first chapter, or the first lecture, that those limits in distribution of those lengths we could do by hand using Earn models in the setting of the binary trees, and we got precisely Aldous' line breaking construction out of that. So that matches up the two definitions that I've given of the Brownian CRT. Okay, so I think a comment is in order about the sort of special role that this binary case is playing here. Right, so we've got this whole universality class of random trees which are in the domain of attraction of the Brownian CRT, if you like. And within that class, this particular family of binary trees are playing a kind of distinguished role because they're basically already sitting inside the Brownian tree, right? If I pick the root and K-uniform leaves, and if I think just about the combinatorial shape that that gives me, it's giving me precisely the law of one of these trees generated by Remy's algorithm. There's no approximation there. It's already sitting there inside the limit object, right? And that's the reason that one can in fact prove an almost sure version of the convergence theorem in that case. I'm not going to do it in this lecture course, but one can do that, and that's in the paper of Curien and us. Okay, so the point is that this is somehow, if you like, a canonical model within this class because it's sort of already sitting embedded in the limit object. Okay? And everything else is sort of just an approximation of that, if you like. Okay? And I can't tell the difference asymptotically in terms of distribution. Okay? And hopefully in the last lecture I'll get time to mention something about stable trees, and there's an analogous result there. There's some particularly nice family of random trees which converge almost surely to the stable tree rather than just in distribution. Okay, so I think that's what I wanted to say about that. So I've got about 3 minutes, so I just want to say one last thing about the Brownian CRT before we move on to graphs in the next lecture. So let's put that over here. So I again want to sort of refer back to this binary model, which is particularly helpful in many ways. Okay, so the binary trees, they've also just got lots and lots of symmetries, which makes them particularly pleasant to work with. You know, I can relabel things left, right, and center, and I don't change the law. And one particular relabeling that I could do is I could swap the label of the root with any of the other labels on the leaves, 1 up to n. And you can see that in the finite case, that's again not changing the distribution of the object that we get, right? So you can see that the root, although I sort of defined it by convention not to be a leaf, it is actually playing exactly the same role in the object as any one of the other leaves. Okay. So that gives me, I mean, that property sort of goes through to the limit. Okay? And so in particular, it says in the limiting case that if I were to pick a point from this measure, okay, so which is my notion of a uniform point in the tree, and suppose I were to reroute at that point, I don't change the distribution of the object that I'm looking at. Okay, so if I forget about the old root and just take this new point as my new root, then I've got, again, a Brownian continuum random tree with the usual notion of a root. Okay, so we've got this sort of invariance under random rerouting, we would say. And that's a really useful property. It means that I can afford to just completely forget about the root if I like, because I can recover a root at any time just by sampling a uniform point in my object. So let me just write down a couple of lines about that. So invariance under random rerouting. Okay. So for the trees Tn2, any permutation of the leaf labels gives it a tree with the same law. And similarly, can swap the label of the root with that of any of the other leaves. Is everybody happy with that? That, you know, if I just sort of swing this picture around, I'm really just getting the same picture all over again. Okay, so. Okay, without altering the distribution. So in the limit, this entails that the Brownian CRT is, or its distribution, let's say, is invariant under random rerouting. Under rerouting at a point chosen according to this measure mu2e. Okay, and so that's something we're going to use quite a lot in the next lecture. Okay, so there's a much more detailed description of the things that I've just sort of sketched my way through in chapter 5 of the notes. And I've also put in some stuff about the fractal properties of the Brownian CRT. So this is a random fractal. There's lots of self-similarity going on here. You can kind of see that even actually in this binary tree setting. So think about the split that we had of the tree into 3 subtrees, which was caused by looking at the subtree up from the root to the branch point, and then from the branch point to the label 1, and the branch point to the label 2. So we saw that was a way of splitting the tree into 3 little subtrees, each of which was again evolving according to Remy's algorithm. So that tells you that in the limit, what are you getting? You're getting 3 little randomly rescaled Brownian CRTs glued together at a common point. Okay, and of course, the factors by which I'm randomly rescaling, those are dependent on one another. The numbers of leaves falling in each of these 3 subtrees obviously have to sum to n. Okay, but nonetheless, I'm getting nice scaling properties for the object that we get. So that's a way of saying that this object is a random fractal. It's got little copies of itself inside of it. Okay, and I go into that in much more detail in the notes and give a proof that the Brownian CRT has Minkowski dimension too. Okay, so I'll finish there for today. Thank you very much.